Hello class, welcome to the Stat 215 Lecture 20 video. In this video, we are going to focus on three objectives. First, we want to define the sampling distribution for a sample proportion. Second, we want to construct the confidence interval for a population proportion. And third, we want to construct a confidence interval for the difference in two population proportions. Let's begin with our first objective. To start our first objective, let's look at a motivating example. Suppose we have data from all 3,945,102 live births in the United States in 1998. We can see a display of this in the graphic below. One of our variables along the x-axis is the gestational age. Second, we have babies born before 37 weeks. This was highlighted in purple, the rest in kind of a yellow gold color. Using that information, we can see that 11.6% of the babies were born premature in this population. So for our sampling distribution of a proportion, we can suppose that we have 1,000 random samples of size n equal to 100. 1,000 values for sample proportion is p hat. That little caret, we say it in statistics as hat. Notice that it's symmetric, our graph that is, and it sort of looks like the normal distribution. And it is centered at our population proportion, which is approximately 0.116, with a standard deviation of 0.032. So the rule for our sampling distributions for proportions is that we let p equal the probability of success. Remember, success is the event of interest that has happened. It's not always necessarily the win. And p is the proportion of success in the population. And we define q to be 1 minus p, or the probability of failure. We let n be the sample size of the repeated samples. And under certain conditions, the sampling distribution of the proportion follows a normal model with a mean equal to p and a standard deviation equal to the square root of pq over n. In other words, our sampling distribution of p hat, which is our proportion of our sample, should approximately follow the normal distribution with mean p and standard deviation square root of pq over n. We can see a drawing of our theoretical normal distribution below. Let's go back to our example for our premature births. So we are given that p equals 0.116 and a sample size of 100. This means the standard deviation of p hat is equal to the square root of pq over n, which would equal the square root of 0.116 multiplied by 1 minus 0.116 divided by 100, which would equal 0.032. So again, this would mean for our sample proportion, we have a mean of 0.116 and a standard deviation of 0.032. Let's talk about the usefulness of the sampling distribution. So what is the probability of taking a sample of size 100 and getting a sample proportion of preemies equal to 0.2 or more, meaning 20% more preemies in the sample? Well, we could find the probability greater than 0.2 for our normal model with a mean of 0.116 and standard deviation 0.032. This is something we already knew how to do. In fact, we can do this in StatCrunch. So if we want to find the probability of p hat being greater than 0.2, we can easily find that the answer to this would be 0.0043. How? Well, using our normal model in StatCrunch, we can plug in that we have a mean of 0.116 and a standard deviation of 0.032. We would put in greater than or equal to as our sign and 0.2 as our x value and hit enter, and we will get our corresponding probability of 0.0043. This means about 95% of p-hat values are between 0.052 and 0.18. So 0.2 or more does not often occur. We can even see this visually in our normal distribution curve. Speaking of our normal model, we should talk about z-score. So as we know, p-hat is going to approximately follow the normal distribution with mean p and standard deviation the square root of pq over n. In our example, this means that it was following the normal distribution with mean of 0.116 and standard deviation of 0.032. As you recall, we were asked to find the probability that p-hat was greater than 0.2. We could also use this with our z-score. How? Well, our z-score formula, if you recall, was z equals x minus mu over the standard deviation sigma. By plugging in 0.2 for x, 0.116 for mu, and 0.032 for sigma, we can find a z-score of 2.63. This implies that the probability of p-hat greater than 0.2 is going to be equivalent to the probability of z greater than 1.63. If you recall, in the z-table, we can't find probabilities directly that are z greater than x, but what we can do, z greater than z, we can use the complement rule and do 1 minus the probability of z less than or equal to z. So in this case, that would be 1 minus 0.9957, which would give us a probability of 0.0043. This is the same value that we were given using StatCrunch. This brings us to our second objective, to construct a confidence interval for a population proportion. So first we want to know, what if we don't know what P is? As you recall, we don't particularly or usually know true parameters for our population. So in this case, because we're talking about proportion, that would imply that we typically don't know what our population proportion is. So instead, we have to estimate it. And if we can recall, we know that the probability of negative z alpha over 2 less than z alpha over 2 is equal to 1 minus alpha. And we can recall from a few slides previously that z equals p-hat minus p over the square root of pq over n. Remember, this is just equivalent to our traditional z formula, only we adjusted it for our values when we're using proportions. So this would imply that a 100 times 1 minus alpha % confidence interval for p would be the probability of negative z alpha over 2 less than p-hat minus p over the square root of pq over n less than z alpha over 2, which would be equivalent to 1 minus alpha. The result, when n is large, would be, as we stated previously, well, not quite previously, I should say, when n is large, we would say that the probability of negative z alpha over 2 less than p-hat minus p over the square root of p-hat q-hat over n. Notice the hats. That's saying because we still don't know the true proportion, or and also the true proportion of failure, we would estimate using our population proportion, which would be less than z alpha over 2, which would be equivalent to 1 minus alpha. So therefore, In our case, the 100 times 1 minus alpha % confidence interval for P is going to be P hat plus or minus Z alpha over 2 multiplied by the square root of P hat times Q hat over N. Now, at this point, you're probably saying, okay, but what does it mean when we say N is large? In this case, when N is large, we mean that the values N times P hat must be greater than or equal to 5, and N times Q hat must also be greater than or equal to 5. This is one of those assumptions that we must follow or check. At this point, let's go ahead and take a look at an example. In a random sample of 500 families living in Pittsburgh, it is found that 340 subscribe to HBO. We want to find a 95% confidence interval for the actual proportion of families in Pittsburgh that subscribe to HBO. Now, first, we need to record what information we have. We have a sample size of N equals 500. Our P hat is going to be 340 over 500, which will be equivalent to 0.68, and Q hat, which equals 1 minus 0.68, which would be equal to 0.32. We are asked to find a 95% confidence interval. This will imply that alpha equals 0.05 and alpha over 2 will equal 0.025. Now, if you haven't memorized it already, you may use the z-table or StatCrunch to find our z alpha over 2. In this case, it would be 1.96. So at this point, we have all the information we need in order to calculate a 95% confidence interval for P. We would plug in to our formula of P hat plus or minus z alpha over 2 multiplied by the square root of P hat Q hat over N, and we would get 0.68 plus or minus 1.96 multiplied by the square root of 0.68 multiplied by 0.32 over 500. This would simplify for our 95% confidence interval to be 0.6391 to 0.7209. Again, if you haven't memorized these very common critical values for the normal distribution table, I highly recommend you do so. All right, before we move on to the next slide, I do want to highlight a couple things. So first off, I didn't check that assumption about having NP and NP hat and NQ hat greater than or equal to 5. This is one of those assumptions that you don't always necessarily need to work out by hand. A lot of times it's just a very logical thing. So if we scroll back up to our problem, and it says it is found that 340 subscribers we already have 340 subscribers to HBO out of the 500. That means that N P hat is 340. And logically, without doing the math, I know that 500 minus 340, which would be our N Q hat value, is going to be obviously greater than or equal to 5. So I don't actually need to go through and calculate it out by hand to get that exact value. I just need to know that it's going to be greater than or equal to 5. Okay, so let's go ahead and talk about our choice of sample size. So if you recall, our margin of error, abbreviated with ME, is equal to Z alpha over 2 multiplied by the square root of P hat Q hat over N. And we want to know what sample size is required to ensure a certain margin of error for a given confidence level. You may recall we did the same thing when we were talking about sampling distributions for means. In this case, N is going to equal to Z alpha over 2 squared multiplied by P hat times Q hat over our margin of error squared. This leads us to talk about our second example. How large of a sample size is required if we want to be 95% confident that our estimate of P in example 1 is within 0.02 of our true value, or in other words, within 2% of our true value? By plugging into our formula, Z alpha over 2 squared multiplied by P hat Q hat over ME squared, we would have 1.96 squared multiplied by 0.68 multiplied by 0.32 divided by 0.02 squared. This would give us 2089.8. Now, because sample size cannot be a fraction of amount, we're going to need to round up to our nearest integer. So therefore, we would need a sample of 2090 to ensure our margin of error is no larger than 0.02. Very good. Let's keep going. So for a more general case, you don't know a good choice for P hat before you take your sample. Recall, our margin of error is Z alpha over 2 multiplied by the square root of P hat Q hat over N. Our choice of P hat equal to 1/2 is something that's going to maximize our margin of error, meaning it's going to be the worst you can do. The reason for that is because if P hat is 1/2, that means our PQ, or excuse me, our PQ, if our P hat is 1/2, that means our Q hat will also have to be 1/2. If we use our formula, we can illustrate that N equal to Z alpha over 2 squared multiplied by 1/2 multiplied by 1/2 over ME squared is going to equal Z alpha over 2 squared divided by 4 times the margin of error squared. This results in a margin of error no more than the value of our margin of error you select, no matter what P hat turns out to be. Okay, so this brings us to objective 3. We want to construct a confidence interval for the difference in two population proportions. But before we do that, I want to circle back to our first example because I realize we forgot to do something. Can anyone guess what we didn't do? We didn't interpret. And to me, that's one of the most important steps. So let's go back and do that now. We calculated that our 95% confidence interval for P was 0.6391 to 0.7209. This means one option for our interpretation could be we are 95% confident the true proportion and we can scroll up if we don't recall, of HBO subscribers in Pittsburgh is between 63.91% and 72.09%. Very good. Notice this follows a similar format as we did when we interpreted confidence intervals for means, only instead of using true mean, we use true proportion. Okay, now we can go ahead and move on to our third objective. That is constructing a confidence interval for the difference in two population proportions. So if you recall, when we did a confidence interval for two means, we had two samples, two populations. The same thing is going to be true in this case. We'll have two populations, two samples. We'll have our population proportion P1 and our sample proportion P1 hat. We will have our population proportion P2 and our sample proportion P2 hat. Our new parameter of interest is P1 minus P2, which will imply our new statistic will be P1 hat minus P2 hat. Now we can start talking about our confidence interval for P1 minus P2. We know that P1 hat is a normal random variable with mean P1 and variance P1 times Q1 over N1. This is just an extension of what we did in Objective 2. Similarly, P2 hat is a normal random variable with mean P2 and variance P2 times Q2 over N2. This implies that P1 hat minus P2 hat is also going to be a normal random variable. We will know that our expected value of P1 hat minus P2 hat will be equivalent to the expected value of P1 hat minus the expected value of P2 hat, which will be equivalent to P1 minus P2. And our variance of P1 hat minus P2 hat will equal the variance of P1 hat plus the variance of P2 hat, which will equal P1 times Q1 over N1 plus P2 Q2 over N2. Using this information we derived, we can say that when n is large, the probability of negative z alpha over 2 less than P1 hat minus P2 hat minus P1 minus P2, each of those their quantities, divided by the square root of P1 hat Q1 hat over N1 plus P2 hat multiplied by Q2 hat over N2 is going to be less than z alpha over 2, which is going to be equivalent to 1 minus alpha. Therefore, our 100 times 1 minus alpha % confidence interval for P1 minus P2 is going to be the quantity of P1 hat minus P2 hat plus or minus z alpha over 2 multiplied by the square root of P1 hat multiplied by Q1 hat over N1 plus P2 hat multiplied by Q2 hat over N2. And once again, what do we mean by n being large? It is once again an extension of what we did in Objective 2, where we found that np hat and nq hat had to be greater than or equal to 5. That is still the case, only it must be true for each of our samples. So we want n1 p1 hat, n1 q1 hat, n2 q2 hat, and n2 p2 hat, but all have to be greater than or equal to 5. At this point, let's take a look at an example to wrap up this lecture. In the study, Germination and Emergence of Broccoli, conducted by the Department of Horticulture at Virginia Tech, a researcher found that at 5% Celsius, 10 broccoli seeds out of 20 germinated, while 15 out of 20 germinated at 15 degrees Celsius. Compute a 95% confidence interval for the difference between the proportions of germination at the two different temperatures. Is there a significant difference between the two proportions? So let us have group 1 be our 5% Celsius and let group 2 be our 15% Celsius. Again, we are asked to find a 95% confidence interval for P1 minus P2. So we should identify all of our relevant information. So N1 will be 20, N2 will also be 20. P1 hat will be 0.5, Q1 hat will be 1 minus 0.5, or also 0.5. P2 hat will be 15 over 20, which will be 0.75, and Q2 hat will be 1 minus 0.75, which will equal 0.25. At this point, we have all the relevant information to calculate our confidence interval. If we simplify and type into our calculators correctly, or alternatively use StatCrunch, we will get a 95% confidence interval of negative 0.54 to 0.04. This means that if we scroll up to our first question, we want to compute a 95% confidence interval for the difference between the proportions of germination at the two different temperatures. That means that the true difference between the proportions of germination at temperatures 5% Celsius and 15% Celsius goes from negative 54% to 4%. Just as when we were comparing the confidence intervals for two proportions for means, if our 0 is in the interval, that means we cannot say there is a significant difference between our two populations. So in this case, 0 is in the interval, so we cannot say that P1 and P2 are different at the 95% confidence level. Okay, so at this point, this brings us to our end of the lecture. Once again, I just want to do a quick review of things we've learned. So we've learned that when n is large, our confidence intervals for P and P1 minus 2 can be constructed using the normal distribution. We learned our two confidence interval formulas for P. For P by itself as a single sample, it's P hat plus or minus C alpha over 2 multiplied by the square root of P hat Q hat over N. When we are calculating a confidence interval for two proportions, P1 minus P2, our confidence interval is going to be the quantity of P1 hat minus P2 hat n quantity plus or minus Z alpha over 2 multiplied by the square root of P1 hat times Q1 hat over N1 plus P2 hat multiplied by Q2 hat over N2. Okay, that's the end of this lecture. As always, if you have questions, send me an email, and have a good night.